Once you check your conditions and you're convinced that a linear model is indeed appropriate for your data and is appropriate to model the relationship between your response and your explanatory variables, the next step is to check the fit of your model. In other words, how well it fits your data. And for that, we introduce a new measure called R-squared. Strength of the fit of a linear model is most commonly evaluated using R-squared. This is calculated as simply the square of the correlation coefficient. The R-squared tells us what percent of variability in the response variable is explained by the model. The remainder of the variability is explained by variables not included in the model. And then the R-squared value, being the square of the correlation coefficient, is going to be a number that's always between 0 and 1, that corresponds to the percentage of the variability in the response variable that's explained by the model. If you know your correlation coefficient, calculating R-squared is easy. But how do we interpret it? Which of the following is the correct interpretation of the R-squared for this model for predicting percentage living in poverty from percentage of high school graduation rate? And remember that R-squared was 0.5625. A. 56.25% of the time, percentage of high school graduates predict percentage living in poverty correctly. This basically is implying that 56.25% of the data points are going to be exactly on the regression line, so predicted accurately, versus the remainder not. But note that R-squared is not about what percent of the data actually fall on the regression line. So this is not a correct interpretation. B, 43.75% of the variability in the percentage of residents living in poverty among the states is explained by the model. This is starting to sound right, but the value is simply not right. Here, this is the complement of R-squared versus what we would really want is for R-squared to be explaining the percentage of the variability in the response variable. So this is not the correct interpretation either. C, 56.25% of the variability in the percentage of high school graduates among the states is explained by the model. This is not correct because this is about the explanatory variable, not the response variable. D, 56.25% of the variability in the percentage of residents living in poverty among the states is explained by the model. This is indeed the correct interpretation of R-squared, the percentage of variability in the response variable explained by the model. Let's take a look at another example. The R-squared for the relationship displayed in the scatter plot is 92.16%. What is the correlation coefficient? Since going from R to R squared, we simply square the value. Going from R squared to R, all we need to do is take the square root. So square root of 0.9216 actually yields 0.96. But could this be the correlation coefficient for this relationship? The answer is no, because there is clearly a negative relationship between these two variables. Therefore, the correct correlation coefficient would be negative 0.96. Remember, if you square negative 0.96, you're still going to get positive 0.9216. So when you're going from R squared to R, you want to first rely on your calculator or computation to give you the numerical answer, but then you want to look at the relationship between the variables, a scatter plot of the relationship, in order to determine whether the sign of that correlation coefficient should be positive or negative.